Here's a probability question. Let's suppose we have a piece of code that can generate a random face. These are some random faces generated by the lovely site thispersondoesnotexist.com. Let's also suppose we have some neural network classifier which takes in a face and guesses the mood of the person. These sorts of classifiers usually return a set of probabilities. It might say, for example, I guess that this face is happy with probability 80%, sad with probability 15%, and so on. Now here's an interesting question. How might we generate a random happy face? Or if we have some other neural network that guesses the age from a photo, how might we work out the average age at which people are happy? If you think like a programmer, you might say, easy, I'll just keep generating faces, feed them into the mood classifier, and if the happy score comes out high, then I'll stop and return that face. And then someone asks you, how high does the score have to be? And you say, I'll leave it as a parameter that the user can set, to hide the fact that you have no idea. If you set the threshold too high, then your routine will be slow because maybe not too many faces are happy. If you set it too low, you'll let too many unhappy faces through. Okay, so the naive programmer's approach has some issues. Let's try and be clever and think like a probabilistic modeler. We might say, the mood classifier returns a vector of probabilities, so let's define a discrete random variable, let's call it y, which takes value happy with probability 80%, in this case, sad with probability 15%, and so on. This is called the categorical distribution. Then we can interpret the question as asking for a conditional probability. If big X is a random face, we just want the conditional distribution of big X conditional on y equals happy. In terms of the likelihood function, we want the likelihood of an arbitrary face little x conditional on y equals happy. Bayes' rule tells us how to work out a conditional likelihood, so we're done, we've solved the problem. Probability modeling is lovely because once we can learn to express our questions in the language of probability, then all sorts of things just magically resolve themselves. Here, we don't have any nasty arbitrary threshold parameters to choose. But, there's always a but. The answer we just gave, find the conditional likelihood using Bayes' rule, is just plain useless, because A, it's usually intractable to apply Bayes' rule as we saw, and B, even if we could derive the conditional likelihood, we still don't know how to sample from it, and the question asked us, how should we generate a random face? It didn't ask us what's the likelihood of a face. The happy path is to combine the two approaches. Take a little bit of the programmer's spirit which says, hey, I have code that can generate X's, let's use it. And take some of the mathematician's spirit, which has a very deep and rigorous understanding of what conditioning means. When we do this, when we combine the programmer and the mathematician, we get computational Bayes' theorem, which is the topic of this video. The technique we're going to see is very, very simple to use. It's just 4 lines of code, but there's so much thinking behind it, and that's what the real focus of this video is, to get you to understand intuitively why these 4 lines of code are the right thing to do. Let's start with a refresher on conditional distributions. Here's a pair of random variables x and y written in code and also shown as a joint likelihood plot. This code first generates x uniformly in the range -1 to 1, and the top plot shows the marginal distribution of x. Now, remember the big idea of conditional distributions. If we take a horizontal slice through the joint likelihood, let's say we take the slice at y equals 0.2, and then we rescale this slice so it integrates to 1, what we get is the conditional likelihood of x conditional on y equals 0.2. Okay, so that's a refresher about what conditional distributions are. Now let's look at the computational Bayes method. Here are the steps to use. First step, generate a sample x1 up to xn from the x distribution. Here's code to generate a sample of size n equals 1000. I'm plotting the sampled values here, one line, one vertical stroke for each xi. This type of plot is called a rug plot because it looks like the tufts on a carpet. Next step, we compute a weight w subscript I for each one of these sampled x values. Let wi be the conditional likelihood of the observed y value, conditional on x taking value little xi. Next, rescale the weights so they sum to 1. Here it is in code. In this particular example, y is normally distributed with mean x squared, so I let w be the PDF of the normal distribution with mean x squared. I'm evaluating the PDF at y equals 0.2, the y value that we're conditioning on in this picture. In the diagram on the right, I'm showing the sampled x values again, and I'm color coding them by the weight wi. Now we have sampled x values and each xi has an associated weight wi, and the rule for approximating conditional probabilities is simply this. The probability that x lies in some set A conditional on the observed value y is the sum over all sample points xi that fall in set A, the sum of the corresponding weights wi, here written with indicator notation. Let's make that more explicit. Let's say I wanted to plot a histogram of the conditional distribution of x conditional on y. To plot a histogram, what I'd do is I'd first of all split the x-axis into bins. Let's call them bin 1 up to bin m. Then, for each bin, I want to know what's the probability that x falls in that bin. The rule on the right says the conditional probability that x falls in the bin is the sum over all sampled values xi in that bin of the weights wi. When I simply apply that, it gives me this histogram here. In fact, this is just a one line of code. Matplotlib has a built-in function plot.hist which accepts a list of weights, and it just adds up the weights for each bin and plots the total. I'm doing one extra little thing in this plot. I use the extra argument density equals true, and this rescales the bar heights so that the total area of the plot is equal to 1. This is called a density histogram, and it's convenient because then the y-axis is directly comparable to the PDF plot. You can see here the histogram we got looks very similar to the PDF on the left-hand side, and the scales are the same. You may be able to work out from these pictures why this computational procedure works. The picture might perhaps be a bit misleading though, because I've chosen a uniform distribution for x in this example. But the procedure works whatever the distribution, and at the end of this video we'll see a proof. Two more things to take note of. First, there's also a conditional expectation version of the formula. If I want to work out the expected value of some readout function h of x conditional on y, I take the weighted sum of h of xi. You should remember from the last video about Monte Carlo this idea of expectations of readout functions. In that video we saw that the probability formula is in fact just a special case of the expectation formula. The next thing to note is that this method I've described is actually just one way of doing Bayes' rule by computer. It's a brute force method. It's really simple and you can use it pretty much everywhere, but sometimes it takes very many samples for it to be a good approximation. Basically, any specialist field of machine learning will have its own specialized numerical methods, and it's just the same with Bayesian machine learning. So there are other more sophisticated ways of applying Bayes' rule that people have come up with. There's one method in particular called Gibbs sampling that you'll come across later. But for now, I just want to focus on this simple basic three-step method. Let's work through another example. Here's the question. Consider the following probability model, which has two random variables, theta and y. Suppose we've observed the value of y, and we want to know the likely range of theta, conditional on y. Let's just apply the three-step method. Step 1. Generate a sample of x values. Actually, in this problem, the variables are theta and y, not x and y, so we want a sample of theta values. I'll call it theta sump. Step 2. Compute the weights. based on the conditional likelihood of y. The question tells us how y was generated. It says y is binomial with parameters 3 and theta, so this is its likelihood. Now, just evaluate the likelihood at each of the sampled theta values. We might as well ignore the 3 choose y factor at the front because it doesn't depend on theta, so it will cancel out when we rescale the weights to sum to 1. Step 3. Whatever we want to report about the conditional distribution of theta, report it via this weighted sample. Here I'm plotting a density histogram to show the conditional distribution of theta. I'm also showing an unweighted histogram to show me the original distribution, which was uniform. Okay, that's all there is to computational Bayes. Now we have everything we need to answer the questions we posed at the beginning of this video. Let's suppose we have code that can generate random faces, and we have a mood classifier that guesses the mood of a face, and which returns a list of scores for each mood, which we'll interpret as a categorical random variable. We'll imagine that the true mood is a random variable big Y, and the probability that the true mood is happy is 0.8, and so on, at least for this particular face little x. Let's answer the second question first. What age are people happy? First step, generate a random sample of faces. Next step, compute a weight for each face in our sample. The weight should be the likelihood of the outcome y equals happy, conditional on a given face xi. Next, the question asks us, what age are people happy? Which we can interpret as a conditional expectation. In other words, find the expected value of h of x conditional on the outcome y equals happy. And we can just approximate it by the weighted sum here. Okay, so that's all exactly the standard steps that we've laid out already for any computational Bayes question. But the other question is something slightly different. How should we generate a random happy face? I'm just going to tell you the answer for now. Pick one of our faces in the sample at random, but weighted according to W. Maybe it's obvious to you that this is the sensible thing to do. Maybe it's one of those things that's on the tip of your brain. It seems nearly obvious, but you can't quite pin down exactly why. After we've studied section 6.3 on empirical distributions, I hope it'll become clear. Okay, so this is computational Bayes. Let's just go back and recap the mathematical way of using Bayes' rule so we can compare and see why this computational method is so useful. This is a recap of section 4.2. The first step in applying Bayes' rule mathematically, write out the marginal likelihood function for x. Step 2, write out the Bayes' rule formula. We usually write it out this way with a constant kappa in front. Kappa is whatever it has to be, so that to make this into a legitimate probability density function. And just a reminder of where this formula comes from. It's the product of two likelihoods, the likelihood for x and the conditional likelihood for y, and that's just the joint likelihood function. We're taking a slice of the joint likelihood function, and we need to rescale it to be a valid PDF, and that's what the kappa is for. So now we've found the conditional likelihood of x conditional on y, and we can do whatever we like with it. There are two big gotchas here. The first is that it's usually intractable to find kappa. We saw that in section 4.2, even for what looked like a pretty trivial Bayes problem. The second is that sometimes we don't even know the likelihood function for x. In this code snippet here, we know exactly what the likelihood for x is because x is just a simple uniform random variable. But in the example from the beginning of this video, where we called x equals random.face, there's no way we could ever write down any sort of useful likelihood function. Computational Bayes is what comes to the rescue in both of these cases, either where you can't find kappa or where you don't even know a likelihood function for x. To finish off, let's look at the derivation of the computational Bayes method. You certainly don't need to know this, but I'm just including it here because it's fairly simple and it's nice to see how it drops out of the Monte Carlo idea. First, we're only going to bother deriving the formula for conditional expectation. We saw in the last video on Monte Carlo that this formula for conditional probability is just a special case of the formula for conditional expectation, so this is the only one we want to derive here. This is the argument. Start off with the expectation we want to work out. Then I've rewritten it as an integral. This is just the definition of expectation, an integral of the quantity we want times the likelihood of the random variable that we're using. Next, I'm using Bayes' rule to tell me what this conditional likelihood is. I'm leaving it here with a constant kappa to be determined. Next step is just a simple rewrite. The thing we want to integrate has a term PR sub x, which I'm going to keep, and I'll gather everything else into a single function, call it g. So what we've produced is the integral of g of x times the likelihood of x, which we can rewrite as just the expected value of g of x. Finally, Monte Carlo tells us that we can approximate it by the average of g of xi, where the xi are a sample drawn from distribution x. The formula for g involves this constant kappa, so now let's turn to kappa. Kappa is whatever is needed to make the conditional likelihood of x integrate to 1. I've written it here as 1 on kappa equals this integral over x. Let's do the same thing as we did before. We'll write it as an integral of some function f times the likelihood of x. In other words, we'll rewrite it as an expectation. And we can use the Monte Carlo approximation once again to approximate this expectation. So let's summarize what we've got to. The conditional expectation that we're after is approximately the mean of g of xi, and plugging in the definition of g, this is what we have. Now plug in the approximation for kappa. This term in brackets that we've produced here is simply the weights wi, incorporating a rescaling that makes the wi sum up to 1. So we get to the answer we wanted. The proof is complete. As I said, you don't need to know this derivation to be able to use it, but it's good to see it, and it's good to get a sense of how the Monte Carlo approximation can be used in a more sophisticated setting. It's completely impossible, by the way, to take all of this in just by looking at it. So what you should do now is write out these two expressions on the left, the conditional expectation and the one on kappa, and then turn off the screen and see if you can reproduce all the argument. YouTube videos are great for watching, but you only learn to do maths by doing. Okay, so now we know how to apply Bayes' rule. We know how to apply it with maths, and we know how to apply it by computer. The next thing is to see why Bayes' rule is such a useful tool for making sense of the world, for drawing inferences, and for testing our hypotheses in the light of data.